Hello, my name is Gabriel Kelman, and today I will be walking through the Fluent Project 2, where we do airflow over a flat plate. So first thing we're gonna do, these first two steps are pretty easy. We're gonna open this up. I already have them open in other tabs just to make this go faster. I won't be showing you won't be starting from scratch. I'll just show you exactly what I did. So to start, you have to obviously make your plate. So to make your plate, you go here, you use this rectangle tool, start at the origin, go out, just make things easier, and then you would have your plate. And after that, you would want to make sure it's in the right dimensions, the horizontal being this side, vertical being this side. The vertical side doesn't matter an insane amount because you did not specify, but for the horizontal, you come here, you make it your height, which is 1 meter. The instructions label it in 100 centimeters, but I kept it in meters and just converted the 100 centimeters to 1 meter just for simplicity, and just to make life a little easier. So yeah, here you can see my dimensions: 1 meter, 0.5 meter, and then after you do that, you come up here, and then you do surface from sketch, and then you would end up making this, and then that's pretty much it for this step. After that, you come here, open this up. Again, I already have it pulled up. So after you get it here, this is where things take a little longer. Yeah. So the first thing that I did, as you can see on the left hand side right here, is I clicked this entire surface using this surface tool up here, and started a face mesh. And here you can see these, what was it? The settings I used: one face, not having suppress, map, quadrilaterals, and keeping these as no. After you do that, you start with the edge sizing. You do your top and bottom plate. Also, you want to name these to make it easier. I'll just go over that at the end of this part. So again, after that, you do your number of divisions to do sizing from here to here. Again, click these two, make sure they're selected. Go over here, click apply, suppress number of divisions, and you put whatever number of divisions you want. I chose 50. Behavior hard, and you want to make sure there's no bias. Then you go to your inlet side, and you want to have a new thing there. Start here, number of divisions 60, and this is when things get a little different. You want to make sure you capture this is all hard, and you want to make sure there's a bias. There is a bias this time. You want to make sure you click this one. So you can choose no bias, but again, I just chose this one. And then your bias factor for this one, I chose 70. Yeah. So after that, you go to your outlet side. Do the same thing as you did for the inlet side, except instead of it being this one is going to actually have a reverse bias so that it's towards the bottom. And then after that, what you can do is you can go here, and then you can go here, and you use this tool, click, and then create name selection. I'm not going to do that since I already did it, but just to make sure everything is labeled right, labeled this plate, I labeled this inlet. As you can see, inlet, this is just the entire thing. Outlet, this side, plate is the bottom, and the far field is the bottom because this is not really relevant, because this is just supposed to be over a flat plate. And then that'll be it for this section, and that will be it for our meshing. So after that, you come here, you want to make sure this is double precision, or when you double click it, it'll end up popping up and asking you to do double precision. Again, I already have it pulled up. So here it is. Yeah, so we want to make sure that we have our fluid, or actually we want to make sure that this right here is laminar and nothing else. So again, it's already done. Here's our fluid, our air. and we have our density that is predetermined in the instructions as 1.2 kilograms per meter cubed, and our viscosity as 1 times 10 to the negative 5 kilograms per meter second. And then that'll be it for that part. And then we go down here, fluid. You want to make sure that it's the proper thing. It's air. That's it. Come to boundary conditions here. Wait for this to open. And since there is the free stream velocity, you want to make sure that it has that initial velocity of 2 meters per second, again, as predetermined, because it's the free stream velocity. Everything else stay the same. Keep this as absolute. Okay. And this normal, the magnitude of it is the velocity of magnitude, and it's normal to the boundary as it is going out, and it's going normal, so it's perpendicular directly to the boundary. Outlet here, you want to make sure to prevent reverse flow so nothing ends up going back, because that will mess up your calculations and also just look wrong, and you'll notice it. Symmetry, just have your far field symmetry, and then your wall, you want to make sure it is under no slip conditions, stationary, and no slip, because this will be your flat plate that your air is going over. And here you can see it a little better, the meshing, how up top it's nothing crazy, but when you get towards the bottom, it's a lot more condensed and smaller, to make sure that it's more accurate. As you can see that everything is a lot more closer. All the boxes are closer the further down you go. So also you want to make sure that your residuals are correct and accurate. Here I just did 1 times 10 to the negative 5. You can choose to do smaller, just to make sure you're more accurate. Again, preference, how accurate you want it to be. So then after you're done with that, you go to initialization, and you initialize. This might take a while because for my settings, I chose 10,000 to make sure my calculations are correct. So this might take a minute. So we'll be right back. All right, now we're back from the hybridization, stuff like that. Again, if you wanted to do standard initialization, do it from this, compute from the plate, and have your velocity right here. But we won't do that. After that, you want to run your calculation. Number of iterations, let's put this down just to save time. And then calculate. Here it'll show our, it has already the coefficient of drag already here. I'll show you how to change that in a little bit. So yeah, here's our drag coefficient, our graph for that. You can see relatively constant, but it's a coefficient. Yeah, so here's the report. You want to make a new one. Surface report. Oh, wait, no, not surface report. Sorry about that. Drag coefficient. You pick your zone, and then you click compute. Literally just did that. I'm not going to do it again. Yeah. Yeah. So if you want your velocity vectors, like as instructed in part A, you get the velocity vectors. You would click down here, vectors, velocity, vectors of velocity, color by velocity, velocity magnitude, just all of it, and compute. And like that. Here you can see the velocity looks kind of hard to see from up here, but as you get closer, you can tell that towards the plate, it's a very small velocity. And I mean, it is, if you got really close to it, it'd be 0. And then as you get further up, it gets higher and higher up here. Yeah. You can see here, beginning of the plate, where it's just starting, and then at the end of the plate, the boundary layer is much thicker, so there's less shear. It's farther, and the vertical velocity gradient is increased. So for that, and again, you can do this for pressure. If you want to get, like I said, your pressure contour, you come down here, contour, here, pressure to the contour, pressure, static pressure, same thing, compute, and then skip display. Here you can see that the pressure is really building up over here as it hits the plate, and then it gets decreases and decreases as the velocity increases and increases. Yeah. And then if you wanted to get, oh, and then I think that'll be it for this step. Actually, I lied. That was it for that step. So yeah, I come here, open this, have it open right here. So now we can get our contours again for pressure and velocity. Here, you come up here, all domains. If you want to do your pressure with this, open. Oh, that's why. Apologies. Yeah, there it is. There's our pressure contour. As you can see, high pressure up here, very low pressure at the back. And then you do the same thing for velocity u. Just like that. Here you can see how it's much clearer to see this than versus the vectors, how the velocity increases as you go up towards the free stream velocity, and as it kind of increases here, and then decreases a little bit as the boundary layer, just because it accelerates as it leaves the boundary layer. And there's your velocity contours. And so in the assignment, it asks us to get the velocity profiles at 35 centimeters and 75 centimeters. So in order to do that, we would need to create our line. That's the wrong tool. Line right here, just leave it like that. Here's our point 0, yeah, and 2.5. But here, let me not make a new line, and let me just show you the other lines. Here you go. So at 0.35, let me get rid of this one. So as you can see, this is our line right here. It is 35 centimeters in, and 0.1, I made it for our graph because I'll show you once we get to the graph. It'll make a lot more sense because the graph itself does not look, it makes it look much bigger when I have it at 0.1. Yeah, and then you do the same thing for 75, here. That's fine. We get 75. And again, it'll look better when we get to the charts. Yeah, so here, what you do to create your charts, come up here, chart 3, title it wherever you want. Your data series, you'd be located at 35 or 75, whichever you choose. X, make sure it is your velocity, velocity u, yeah, your velocity x, and then your y is y, and that's about it. I won't make a new one because there's no point, but I'll show you again right here. You can see velocity profile for x equals 75, data series 75, x-axis is velocity u, y-axis is y. Line display, this part relatively simple. As you can see, I capped it at 0.1 because if I went all the way up to 0.5 and everything like that, this becomes extremely small and kind of hard to see. Here you can see the velocity profile and it's kind of linear fashion. You can tell that it's getting larger and larger and larger, so it will start like this and go all the way up diagonally. Here you can see is one of the at the boundary layer when it turns into 2 meters per second. That's once it passed that point, and it is turned into a fully developed flow. Same thing for 35 centimeters. Right here. Oh, sorry, wrong one. 35. Here, I'll show you the data series. X-axis, velocity u, y-axis is y. Same thing, capped it at 0.1 just so it's easier to see. Very linear, but you can tell it's smaller than 75 because it is less developed and the boundary layer is thinner. So its shear has a higher effect on it and holds it back. And then so that'll actually be it for part A and almost all of part B. And so the boundary thickness would actually be at the point again where these bends happen, or actually really when it reaches 2 meters, or not 2 meters, sorry, 2 meters per second velocity, and it reaches that free stream velocity, which would be 0.8 for 0.008 for 35 centimeters, and then 0.0119 for 0.75 meters. And then after that, we come here to our shear stress one. Again, we make it like this. Flat plate. Yeah, so for this one, what I did, which you don't have to do, what I did is I actually made a flat plate right here just to go across the entire thing. And then I went into chart viewer and then I made a new chart up here. Flat plate, general series, yeah, at the location of the flat plate. X-axis is X, and then your Y will be your wall shear. Then after I did that, I exported it into Excel, and then use that for my calculations. Another thing you can do to find the shear stress and friction coefficient is here. You can go to your axes. You want to click wall fluxes, wall shear stress, or in this you use wall shear stress, your X wall because your Y wall doesn't exist, or your skin friction coefficient depending on what you're trying to do. Again, I'm not going to go through them because I already did them. It actually be your direction vector. Click your surfaces. Yeah. And actually, you can just leave it as wall shear stress. And then surfaces. And here you go. You can see your shear stress and how it decreases as the flow develops and gets longer. And then after that, I did the same thing for what was it? For the coefficient of friction that you saw, and then for the coefficient of drag coefficient, come here, which is in report definitions, drag coefficient plate, and then you compute it like I showed you before. And then that should be it. I'm not going to show you the theoretical ones because you can already see because I was not instructed to do that, but you basically just put it into Excel and then you export the data from this, and then you use the equation functions in Excel and the equations given in the project description right here in Excel, and then you put it together. And then you plot the graphs, and then they should look something like this. The only difference is the theoretical, you can't really plot at 0 because for the Reynolds number, you're gonna end up having 0, and then the bottom factor would be 0, and that would kind of mess it up. So you have to do 0.001 for a lot of the things. So yeah, here you can see my final report. Here you can see the shear stress versus theoretical, and coefficient versus theoretical, and then you'll find your coefficient of drag down here when you run your calculations. Doing this. But yep, that's about it. Thank you for watching. Please grade kindly. I'm tired.